Hello YouTubers. Let's check out some of these new and amazing large language models like ChatGPT 4, ChatGPT 3.5, and Gemini Pro as we get them to play the classic game of Prisoner's Dilemma. This experiment explores their thinking and adaptability to this challenging game. The Prisoner's Dilemma is a thought experiment in game theory where two individuals must choose between cooperating or betraying the other without knowing the other's choice in advance. The outcomes vary significantly based on the combination of choices, making it a test of trust and strategy. In our experiment, these AI models played thousands of rounds of the game against established strategies, making decisions to either cooperate or betray. This setup allowed us to observe the large language model's decision-making processes and adaptability in response to changing game dynamics. The results were intriguing. ChatGPT 4 often chose cooperation, aiming for mutual benefit or responding in kind to the opponent's previous actions. On the other hand, Gemini Pro displayed a more varied strategy, sometimes cooperating, other times betraying, showcasing its adaptability. ChatGPT 3.5 started with a competitive edge but adapted to a more cooperative approach as the game progressed. The Prisoner's Dilemma is a game that tests the balance between cooperation and competition. Imagine you and a partner in crime are caught, but the cops don't have enough to convict you both. You can either stay silent, cooperate with your partner, or betray them for a lighter sentence. But here's the catch. If you both betray each other, you both end up worse off. Here's how the scoring works. Betraying is also referred to as defecting. If both players cooperate, they each get 3 points. It's a win-win. If one defects while the other cooperates, the defector gets 5 points, leaving the cooperator with 0 points. But if both players decide to betray each other as defect, they each get just 1 point. This is a lose-lose situation. Our project pitted 20 different classic strategies against the large language models to see how they would react. This included the classic tit for tat, which simply mimics your last move, to more complex ones like gradual or adaptive strategies. Now let's check out the Jupyter Notebook. You can access it via the GitHub site, which is linked below. The first and second blocks are used to import the necessary libraries for ChatGPT or Gemini respectively. In this case, we are setting up the large language model with the OpenAI environment. It uses OpenAI OS, RE for regular expressions, random for generating random choices, Matplotlib for potential data visualization, and CSV and time for logging and timing events. Next, it initializes LangChain's language learning models with an OpenAI API key, setting the stage for AI-driven decisions. The heart of this script lies in the agent class, which encapsulates the behavior and strategy of each participant in the game. Each agent has a name, a strategy function, a history of moves, and a score tracker. Agent A employs a predefined strategy function, analyzing the opponent's history to make decisions. In contrast, Agent B's strategy is dynamically generated using the LLM models based on the game's history, predicting the opponent's move and deciding between cooperation and defection. When it's Agent B's turn, the script crafts a prompt, soliciting advice from the LLM on whether to cooperate or defect based on the game's history. This involves a sophisticated interaction with the LLM's API, where the agent's decision is influenced by the model's response, analyzed through regular expressions to extract a clear cooperate or defect decision. After each round, the script logs the decision-making process and outcomes, providing a rich dataset for analyzing strategies. The next function applied the scoring system we described previously. It culminates in a function called at the end of the game and describes Agent B's overall strategy using the LLM. This offers insights into the AI's strategic thinking and decision-making process based on the accumulated game history and AI responses. In the third block, we define the function, simulate Prisoner's Dilemma, which takes 2 parameters, Agent A strategy and iterations. This function will simulate the game for a given number of rounds using the strategy provided for Agent A. We start by initializing a results dictionary to keep track of all possible outcomes. Then, we create instances of both agents. Agent A uses a strategy function, while Agent B will decide its moves using a language model. Inside a loop, both agents decide on their actions. We then update each agent's history with the outcome and adjust their scores based on the decisions made. This process repeats for the specified number of iterations. After each round, we log the strategy and scores to a CSV file. This allows us to analyze the strategies and outcomes after the simulation. Finally, the function returns the scores for both agents along with their instances. This data can be used to further analyze the strategies and decisions made throughout the game. In the fourth block, we define the functions for 20 classic prisoner's dilemma strategies. I won't describe them now. However, details are provided on the GitHub site, which is linked below. In the fifth and final block, we establish the main loop. First, we define the number of iterations for our game simulation as 50. We are not just looking at one strategy, we've got a list of multiple strategies to evaluate, including tit for tat, generous tit for tat, grim trigger, and many more. Before jumping into the simulation, we make sure to start with a clean slate by checking for and deleting any previous summary files. This ensures our results are fresh and accurate. With everything set up, we begin our simulation. For each strategy in our list, we simulate the prisoner's dilemma game 50 times against a language model agent, tracking the choices and scores of both agents throughout the iterations. To make our results clear and engaging, we plot the scores of both agents over the iterations. This visualization helps us see how the strategies perform over time, comparing the adaptability and effectiveness of each strategy against the language model agent. After each simulation, we dive deeper by requesting a description of the language model strategy. This insight allows us to understand the rationale behind its decisions, providing a richer analysis of our simulation results. We also log these descriptions and scores, ensuring we have a comprehensive dataset to review later. And finally, the results. This experiment produced a lot of interesting data, which I will do my best to summarize. Let's start by looking at the overall score comparing the models. I'm presenting the overall score based on the scoring system described previously. I'm also providing an adjusted score, which is the LLM score minus the score from the established game strategies. The adjusted score factors in the performance of the established game strategies. The overall score puts ChatGPT 4 as the winner, followed by Gemini Pro and ChatGPT 3.5. Interestingly, the adjusted score puts ChatGPT 3.5 as the winner, as it seemed to play a more adaptive game against the established strategies. GPT-4 following closely behind and Gemini Pro losing against the established strategies. Note that repeating the gameplay with the same parameters does not produce identical results due to the nature of LLMs, however their performance is reasonably consistent. There are a lot more details on the GitHub site linked below. I hope you found this interesting, and if this generates some comments below, I might apply this test to future LLMs as they are released. Please like and subscribe and all that usual YouTube stuff. Have a great day.